Peter and Paul, thank you so much for the opportunity to talk here today. It's been my pleasure to be here. First of all, I want to acknowledge the co-authors, Dave Newport and Brian Atwood of TRI. Dave is our project manager, VP of projects and operations. He is in charge of our commercial operations. Also ran the pilot plant, headed up the running of the pilot plant. Brian Atwood is a senior process engineer, and he does quite a bit of Aspen work, and we want him to train on CPFD as well, but we haven't gotten there yet. Of course, you know the CPFD. We have worked with a number of them. It's been a lot of pleasure to work with them. And if if you like the presentation, the credit goes to this team. If there are any omissions or shortcomings, it's my fault. What I want to do is first go over a basic of technology. I don't want to take up too much time, just give you a little bit of feel for what we do, and then get into the CPFD. What we do is essentially a gasification of different feedstocks. We are feedstock agnostic. Our objective is, we start with black liquor, and originally the genesis of technology was to generate hydrogen for fuel cells. And like all of you know, fuel cells are just a couple of years away from commercialization. And so we've been fighting that battle, and then we started with black liquor, and then migrated to biomass. It's a little more uniform. And the problem with biomass is transportation radius and cost of biomass. And like any capital project, it's a delta between the end product revenue and then the cost of the feedstock. And transporting large amount of feedstock is an expensive proposition. So, the payback is not there. So we really had to migrate to MSW. MSW is obviously the most complex feedstock you can work with. It's highly heterogeneous, and the chemistry is pretty challenging. And of course, you got to deal with a lot of contaminants. So at this point, we got a lot of scars to prove it, but we have gone through a pilot plant and ran about 14,000 hours of different feedstocks. And actually, we went all the way from feedstock to finished product, jet fuel or diesel, spec diesel. So I think that has helped us to develop the technology. This kind of gives you a little bit of feel for what we do. It's a two-stage gasification process. The first stage is indirectly heated. Gasifiers are endothermic, and so essentially we are trying to provide the heat for the endothermic reactions. We have feedstock coming in, and Okay, we have the feedstock coming in here. It goes through drying, devolatilization, and char reactions. And we are generating syngas, and obviously there are particulates, char particles which are generated. We keep, the internal cyclone is a lazy cyclone. The idea is to keep most of the bed material in here and the fine char to leave. And then we collect the fine char here, route it into a second reactor. The reason is char is, is a slower reacting, it's more refractory, and we operate this at a higher temperature and with oxygen so that we can have a faster reaction rate. And the two gases combine together, and that's what goes downstream. And obviously, there are a lot of unit operations, and each part can be modeled separately. And what we are doing is initially just this part. So we have a long way to go. We are in probably the second or third inning of this whole CPFD work, but we got a lot of stuff to do, a lot of options to improve the process. And this is our pilot plant, Pride and Joy. It's actually a 4-ton-a-day unit. we go from, actually you can see the feed system here, and the steam reformer, the CTC, which is the second stage, then the primary gas cleanup unit, then the secondary gas cleanup, which also includes the compressor station, and then the FT unit. This is a standard conventional fixed bed Fischer-Tropsch unit, 3 tubes in there to generate syngas. So what we do is essentially feed 4 tons a day feedstock, take a slipstream of the gas, go through the gas cleanup train, compress it, and then run it into the FT, generate FT fuels, and then we go from there to upgrading the unit. So every part of the commercial operation is represented in here. Originally, we started with just the gasification unit. We said, well, we generate gas, we qualitatively and quantitatively analyze the gas, and if it's clean enough to go into the downstream process, it should be good enough. But then DOE came back and said, no, we want every part of the process to be represented, because commercially, only when you fully integrate the plant and run it, you get valid data and you can scale up reliably, which made sense, but to find money for that was a challenge. But anyway, finally we went through and got all the part of the processes and demonstrated that. Now this is the same setup, except that we also have had the opportunity to work with Velocis, and this is the Velocis reactor right here. It's a microchannel reactor. Obviously this is the fixed bed tall unit versus pretty compact, very efficient, and so we worked with Velocis. We have run a biomass for their commercial demonstration unit and generated again FT liquids. And this kind of tells you what we have generated. This is, we have done MSW, we have done woody biomass, some ag waste, and generated FT liquids in here. And then we also have generated jet fuel and spec diesel. This kind of gives you an idea what the commercial units look like. Right here is our commercial reformer. It's about 105 foot tall total. It's actually sitting on a skirt type bottom supported unit, so it can expand thermally in the vertical direction. These are the 4 heaters, crisscross, which provide indirect heat. This is our typical, what we call first generation heater. It's got essentially plenum and a combustion chamber, and then it's got the tailpipes, what we call resonance tubes, and then the flue gas goes through that. And because we are operating in a pulsating mode, we essentially have a back and forth pulsating flow field, oscillating flow field inside the tubes, which enhances the heat transfer. So you get an order of magnitude improvement in heat transfer, and that way, with limited tubes, we can provide a lot of heat into the process. And this is the site, fulcrum site, where our first demonstration is going to be for this technology, from MSW to jet fuels. It's a 500 ton a day MSW feed rate, dry feed rate. And what you see here, this is a reformer, about 100 foot tall with about 30 foot skirt. And this is our second stage, which is about 40 foot tall, but it's sitting on about 15 foot of skirt. So our goals in Barracuda simulations are basically, we start with proving the performance, what we observe, and then visualize the dynamics of what's going on and validate. At every stage of the way, we want to validate the test. So from small scale to large scale, we want to go through validation of every facet of the process. We also want to do parametric studies and validation, and process optimization validation, and commercial scale validation, and then go into, ultimately what I see is that we want to do real-time process control. Of course, AI is advancing quite a bit. We are working with some companies. We are starting to work with some companies which have the AI software, and basically going to integrating Barracuda, Aspen, and AI to control the process. What's been our development path? Like Peter said, we started working with them in 2008. We've done quite a bit of work. In terms of fluidization dynamics, we have done cold flow studies and validation. And we have done experiments at different scales. And we have looked at, essentially, like PSR has been saying, at every part of the way you have to make sure that your drag coefficient, collision, mixing, segregation models are refined. So we do, actually we have engineered bed material. We work with the bed material, run some cold flow studies and hot studies as well, and get parameters from that based on curve fit, and then use that in the model. And we also have done a tube bundle gridding study. I'll talk to you a little bit later about that. We went through a thermal profile validation. Like Peter said, when they start, it's a cold flow model, then you put in thermal, and then you go into reaction kinetics. So that's what we did. Basically, it's the same kind of sequence. And then we have done steam reforming trials with different feedstock, black liquor, a commercial unit. Then we did the PDU with forest residuals and MSW. And then lately what we have done is to actually do a case study where we did with oxygen feed into the reformer, which is what we do in a commercial unit. What we did was essentially work, typically in a commercial unit, you have a fixed amount of real estate, and you can only put so many heaters because it's a pressure vessel. You can make only so many penetrations because of joint efficiency. So what we have done is to come up with a second generation heater concept where they can pack a lot more heater tubes inside and provide the amount of heat. So in the first generation, we actually use some oxygen co-feed, and then the second generation is all allothermal. So essentially, we are not putting any oxygen into the reformer. And so we have done a comparison of that, and we have done what I call feedstock test reformer. It's a small unit, about 5 pounds an hour feed rate. We did that, we did the testing, and then did the simulation, did the validation of the model, and then extended that to the PDU. We are modifying our PDU, and then we'll run tests and validate that again. And of course, we have done commercial scale reformer simulations. Now, the model is, the idea is you have two different features. One is the physics of fluidization, then you have the chemistry of the feedstock. So you have to marry the two in a model. And obviously, the physics of fluidization depends on a number of factors. We are dealing with unit operating conditions, the hydrodynamics, solids distribution, elutriation, entrainment, and obviously the basic properties of the feedstock, the bed material and the feedstock. The feedstock properties are, essentially is going to dictate the chemistry is changing, the particle sizes are changing, and you have to make sure that you can account for the drying decomposition, the chemical kinetics, both in the homogeneous and the heterogeneous phases. And then obviously you have to look at the interface heat and mass transfer, and of course the heat transfer to the tubes because we have internals in here. And the ultimate objective is to predict the syngas composition, flow rate, carbon conversion, gasification efficiency, and solids carryover rate. And this this kind of shows you the cold flow studies. We have done just a example. The very first cold flow study we did was with at PEMCorp, and we had we worked with Dr. Fred Zenz. And of course, when you talk to him, the first thing he asks is, any question you ask him, he says, okay, have you looked at page 85 of my book? So, it's pretty comprehensive. And so, we worked with him. This this is a fairly large, we were at that time looking at a 2,000 ton a day reformer for woody biomass. And so this was about 25 foot wide and about, it's more like a 2D bed. It's about 24 inches depth. And we had essentially 8 heaters in there, heater bundles in there for a commercial unit. So it's a pretty tall, about 35 foot tall bed. So overall height was about 50 foot. So we were, it had cyclones to return the bed material. So that's where we did the testing. And later, when we started looking at biomass, one of the things we had to look at was the initial models of CPFD were saying the particles essentially go up and then stay there. They're not back mixing into the fluid bed, especially biomass. We have obviously different densities. So did some testing. We did the testing at University of Utah. It's an 8-inch bed and about 24, 26 inches expanded bed height. And you can, I didn't show the simulation because of the time factor, but what it does is in every 10 seconds, in 10 seconds, you start the fluidization. Within about 10 seconds, you can see that it's pretty well mixed. All the particles are, distributed within the bed. And as you increase the velocity, obviously the mixing is better. So we shared all, we did with a number of different feedstocks. This is more like a straw, but then we also did a number of tests with other feedstock, plastics and corn stover and stuff like that. So we shared all the data with CPFD. And this is an 8-inch fluid bed. This is at our pilot plant, and where we did some additional testing, mainly to determine the UMF values and the drag coefficients to refine the drag model and segregation model. Now this is, again, going back to 2008 when we started. The initial model was more or less using blockages, representing about 48 inch of cylinder for the actual heat transfer bundle. So the flow profile was quite different from what you would expect, obviously. Then we actually, this is the coarse grid. Obviously, at that time, the speed was definitely an issue. And, this had about 20 tubes, larger diameter, 8-inch, still not representing the actual case, but it gave us a much better profile, better simulation of the actual cold flow unit. And we then did the actually model of the black liquor reformer. And this was actually a 2-bundle gridding study that I did with Peter. What happened was the actual tube bundle is about 253 tubes, 1.9-inch diameter, or OD. We represented with more like a 61-tube bundle, about 4.4-inch diameter. What I did was kind of use the single-phase analogy to figure out what kind of a pressure drop one can expect, and then we used that kind of approach to model that in CPFD and found that it does a pretty good job. We were able to get good, similar flow pattern, pressure drop, bed expansion, entrainment solid circulation. The big news here is 10x faster than running with this. So at that time, it took a long time to do the simulation, so 10x is a big deal. This is, again, we were trying to do marching into drying, devolatilization, and char reforming studies. We went through a 1,000-ton-a-day unit, did the drying and volatile release, and again, the volatile release indicated that the particles were all migrating to the top. The collision model was changed, and then we did get better mixing. And we also did a char reforming study to make sure our heterogeneous kinetics is correct. All right, what this shows is the black liquor reformer. Essentially, we're looking at a couple of different things, the steam concentration. We put the kinetics in at this point, and you can see CO, CO2, hydrogen, and methane, ethylene, and propylene. So you can see that the red indicates that the concentration is high, but once you get to the top, the concentration is pretty low. And you can see that the CO concentration, CO2, and obviously hydrogen is increasing as we go up to the top. So qualitatively, like Raj said, what we're looking for is qualitative match. Quantitatively also, it did a pretty good job of matching what we expected. So we're pretty happy to see that we are able to predict what we observed in the commercial unit. And this indicates our PDU work with the biomass or forest residuals. What we did take a look at was a thermal profile, and you can see that where the biomass enters, there is definitely a lower temperature. We actually did some cold flow studies where we injected, I used dry ice to represent what happens and put thermocouples to figure out what the temperature decreases in the local zone. So, that gave us a good idea what happens, and the model predicts those kind of, even though fluid bed is supposedly well mixed, you have temperature gradients within the bed. And this one just shows the different species of particles, and you can see that the biomass is pretty well distributed. Obviously, there's a higher concentration of MSW or biomass in here, but then it does distribute. Obviously, the devolverization time scale for these particles is a lot longer than the mixing time. So it's pretty well mixed by the time it releases a lot of the stuff. This is, again, MSW PDU reformer simulation, the full kinetic model. And you can see that, again, we are looking at what happens with particles here. You're looking at biomass content, the char content, and then what you see here is the red indicates moisture being released, and then as the particle gets dry, you can see more blue stuff in here. So this indicates the concentrations of the different species. And again, we were able to validate the model with the actual data from the PDU. I'll skip to the next one. This is a commercial reformer simulation. We did take a look at, again, this is projected numbers at this point. Once we start up our unit at Sierra, Reno, Nevada, we'll have a better idea of how this compares with actual numbers. And this indicates just the fluid dynamics. You can see fairly big bubbles, obviously. Obviously, internals help limit the bubble size to some extent. And so this indicates the mixing, and on the right-hand side, the projections of our gas concentration. This is a comparison of the first-generation heater versus the second-generation heater. In the first top case, we are feeding oxygen and steam into the fluid bed. In the second case, it's all indirectly heated. There's no oxygen feed. And what I'm showing here is really the dry syngas flow rate, steady state. Target is this. My target is actual measurement from the unit, and this is the actual CPFD prediction. So they are well matched in terms of the total mass flow rate. And we have the species and stuff like that. Obviously, I'm not sharing all the details here. What's important in syngas generation, obviously, to produce fuels is hydrogen plus CO. They are the reacting components that are needed for this synthesis. And so what you can see here is the CO plus hydrogen in this case is about 1.9 kilomoles per second, and the model is predicting about 2. Pretty close, about 5-6%. That's to be expected. And the other thing, in this case, when you go to allothermal operation, the second-gen heater mode, we see quite a bit of improvement, about 30% improvement in hydrogen plus CO. So that's a pretty dramatic improvement. One of the big advantages you have then is just with a single first stage, you're able to match or exceed the performance of a two-stage unit. So we're going to be doing tests in the PDU. We already have the PDU model, and actually, I'll go back there. This is the projection for the PDU model. So what it's predicting in the first gen and the second gen, about 25% improvement. Now this indicates the speed. You know, originally when we started, we were right here. It was very slow. It's actually with both hardware and software improvements, we've gone up by 2 orders of magnitude almost. So that's tremendous. And I guess NAT or Dirk is doing quite a bit of fascinating work in terms of cutting back on the time it takes to do simulations. And so you might see another 10x or 100x even. So over a period of time. So that'll be great, because we need all these improvements to do commercial simulations. Commercial simulations use millions of particles, and obviously it's a big unit, and to capture the essence of what the process does, we need faster. So in summary, we have made a lot of improvements, we are learning a lot using Barracuda as a tool. It's very powerful. And like I said, we're in the second or third inning of where we can be. There's a lot of potential I see in using this as a tool to essentially do commercial scale validation and then integrating with AI to enable real-time process control. And it's been, like I said, pleasure to work with CPFD.
All right, my burning question is, you're dealing with a lot of different types of feedstock to this system, it looks like.
Yes.
I'm coming from an FCC background where we know what the catalyst size distribution is going to the cyclone. So how do you set your transport disengaging height? What sets the elevation of your inlets to your cyclones? Does it change much with feed?
Well, what we want is the way we design it is a bed material that we want to keep below the TDH. And of course, biomass, obviously, what's coming through, we want to capture the large particles and recycle back to the bed, but the fines go into the second stage. So we are not really worried about what the feedstock is doing. We are only concerned about the primary material as the engineered bed material that we want to keep. So that makes it a little bit easier to design than trying to worry about feedstock. The real issue with feedstock, obviously, is getting the chemistry, the shape factor, all that stuff is important. But at this point, we are dealing with some gross assumptions about particle size distribution, particle sizes. Thank you.